What we want to attack, kill, destroy today is we are going to focus our attention on isosceles, and equilateral triangles. We're going to use properties of isosceles and equilateral triangles. But first things first, just kidding. We're going to label this. This thing's called isosceles. So the first thing is that we have two sides that are congruent, at least. These are called, well, all of them are called sides, but let me be more clear about that. These are called the legs, or leg. Each of them is a leg. And this over here is called the base. Now, base does not mean bottom. It just means the non-leg. But let's also define isosceles. What does it mean to be isosceles? How would you... All right, the official definition is it's a triangle with at least two congruent sides. What? Hashtag what? What? So an equilateral is also an isosceles triangle. It's just a special one. Good, but not all isosceles are equilateral, just some of them. Good. So 99% of the time when we're talking about isosceles, we're actually talking about something like this. Or rotated around. This is probably the more common way we see it, right? So the two congruent sides are called the base when there are two congruent. And the non-legs are called the base. I think I said something wrong in there. Okay, it turns out that over here, an equilateral triangle, it's kind of like you have an isosceles triangle this way. And then when you rotate it, you also have an isosceles triangle this way. And then when you rotate it, so it's isosceles in every direction. So it technically would be an isosceles triangle as well. But clearly equilateral means a triangle with congruent sides, all congruent sides. So in the family of triangles, this is actually a child of an isosceles triangle. Turns out, and notice that over here it says also label the equiangular aspect. We'll get to it in a minute, but this is also true. This is also true. Over here, as pointed out to us earlier, it turns out that this is going to be true, but we don't know that yet. That's going to be a theorem. And so in this context, we just call them sides. Now, officially, you can say legs. Sure, that's a leg, but so is that one, but so is that one. So at that point in time, differentiating them with a name, it doesn't actually matter. So unless you were somehow being specific and saying, well, I'm talking about these two legs, and this one's my base for whatever reason. But generally, we would just call all these the sides because they're congruent. All right, so we're going to look at two theorems. We're going to prove one of them, and then look at two corollaries. Oh, brand new word. Whoa, bless you. So our very first one. This one's called the isosceles triangle theorem, and sometimes it's called the base angle theorem. Sometimes called the base angle theorem. And it says this: if two sides of a triangle are congruent, then the angles opposite the sides are congruent. Then the angles opposite are congruent. So what does that look like? Well, we have an isosceles triangle. Looks like this. And notice what it says. The given part, the hypothesis is this, that two sides are congruent. Therefore, it's an isosceles triangle by definition. So where does it take us? It takes us to not only those two sides being congruent, but also the angles opposite. Also the angles opposite. So notice the context here. It has to start with an isosceles triangle. It starts with an isosceles triangle. And it ends up with congruent angles. So start with congruent sides, and we get to congruent angles. Hence the name, it's also called the base angle theorem. Why? Because these guys here would be base angles. The angles of the base. Not the angles on the bottom, in this case it is, but just the angles on the base. If two angles of a triangle, let me clean that up. are congruent, then the sides opposite those angles are congruent. So where do we start? We start with the idea of congruent angles like this, and it takes us to also congruent sides. The opposites are going to be congruent. Again, let's be clear about what I mean by opposite. If I'm talking about this angle right here, opposite is directly across, so I'm talking about this side here. So if I were to prove the theorem, let's see how we set it up. Remember that the given is the hypothesis. So we're going to prove this theorem right here. If two sides of a triangle are congruent. So we have to start, the given information is the sides are congruent. So before I do that, I need to have some letters over here. A, B, C. And according to this diagram, which ones are probably congruent? Anybody? Go ahead, just call it out.
A, B, and B.
All right, so AB is congruent to AC. So that's where we're starting, and that's specific to this diagram. It does not matter what letters we call them, but we have two sides that are congruent. And what are we trying to prove? I'm trying to prove that in this diagram, angle B is congruent to angle C. Why? Because those are the sides, the angles opposite the congruent sides. If we were to draw one itty bitty line here, draw this line right here. This one here, like that. But as I draw this auxiliary line, I do need one other piece of assumption, okay? And I'm allowed to. I drew that line, so I can say anything I want about that line, right? So what am I going to say? Not only is those two given by default, but I'm going to say that the green line, and let me put a letter on it over here. So let's say D. That this green line segment bisects the big angle. So segment AD bisects angle BAC. Why? Because I said so. With that in mind, I also know this is true right here. And I'll get to that in a second. And I also know that's true. So when I make the plan for the proof, please tell your neighbor, why are the two triangles going to be congruent? All right, so by way of a plan, we do know that these two triangles are going to be congruent by side angle side, and then by CP/CTC, I'm going to prove that angle is congruent to that angle. And that's the proof. So let's just actually go through it. Statement and reason. All right, since I'm doing side angle side, I'm going to follow that pattern, and I'm going to start with a pair of sides. AB is congruent to AC by given. Then I'm going to attack so that's the pair of sides. Now I'm going to go into angles. So I do know that segment AD bisects angle BAC. That's also given. And as a result of that, and I can throw some numbers in there. I'm going to put a 1 there and a 2 there. As a result, I can say that angle 1 is congruent to angle 2, and the reason for that is definition of angle bisector. Again, if I use a word, there's a 99% chance that I'm going to use the definition of that term in the proof itself. All right, continuing on, the next thing I need is another pair of sides, since that was my pair of angles right there. Now I need another pair of sides, and that would be AD is congruent to itself by our friend the reflexive property. Now we know the triangles are congruent. ABD is congruent to triangle ACD by side angle side. And my last step, I'm off the page, sorry, but that angle B is congruent to angle C by C, P, C, D, C. Okay, let's use these things. So what do we know? Turn the page to numero uno. And what we see here is that we have congruent sides here, which also mean that this angle here is congruent to this angle here. Notice I put a double mark because I don't know if these two are necessarily congruent. They might be, but I don't know. So how am I going to find out? Oh, snap, I can't find anything else. Why is that true? Well, because in this triangle down here, those two sides are congruent, which means this guy here is also n degrees over there. And since we were given the congruence over here, this is n degrees also over there. We don't need to have all that yet necessarily, but I'm going to unpack a little bit further. If I were only to look at the right triangle, what do these two have to be? If you need to see where that came from, we could just say this, that the n plus the 90 is equal to 180. Notice which triangle I'm using. I'm using this triangle right here to do that. Now, we also know another theorem that states that the acute angles of a right triangle are complementary. So I could have said that, where n plus n is 90, but that would be the next step here. So 2n equals 90, so n is 45. So that's 45 there. That's 45 there, which means also this guy up here is 45. My n is 45, and this is a triangle right here. We know the three angles sum to 180, so there's our situation. Now when I combine like terms and subtract, then I could divide and get some great number. What is it? And 67.5. Notice it's a degrees, so it can be decimals or fractions, whatever. If we're talking number of angles, we can't have decimals or fractions. All right, and the last thing we're going to attack, kill, destroy on this lovely day is what is called corollary. Have we defined corollary in this class yet? What a great word. All right, corollary, another word for it is sub-theorem. In other words, as a result of a theorem, what immediately follows because of that theorem? Or what's a special case of that theorem? So, the diagram up here, oh, that's an ugly one if I've ever seen ugly. Okay, the diagram up there was if you have an equilateral triangle, then you also have equiangularage. Made that word up. And this one down here says if you have equiangularage, then you also have equilateralage. In other words, ka-chow! We can make it biconditional because we like biconditionals.